Hi everyone, hope you're doing well. This will be, I guess, a quick lecture just to discuss the basic aspects of group theory. I will not get into that so in deep because it goes way beyond the scope of, of this course, but I can recommend some books. One of them is this, Group Theory and Quantum Mechanics by Michael Tinkham. There are others by Hammermesh, and well, there is a vast literature in groups and applications to quantum mechanics. But in this case, why we are presenting group theory? Because we are interested in representations of rotations by some special groups and the spin in connections with quantum statistics. All right, so but to understand the the main aspects, you need to have a little bit of knowledge on quantum on group theory. So what is a group? What is a group? We can define a group by the following properties. So a group, say a group G, is a set. So we are dealing with set theory, but it's a special kind of set. It's a set of elements. So B, A, B, C, okay? The set of elements. Perhaps a curly bracket is better to represent. So G is a set of elements endowed or with a so-called multiplication operation. Okay. Multiplication can be anything, can be sum, can be matrix product, right? So it's general terminology. It's a, with a multiplication operation satisfying the following. Following properties, all right? The following properties. Associativity. So if you pick up three elements A, B, C of the group, you can multiply them. I'll call the operation by this empty ball here, all right? So this represents the multiplication. A times B times C. It is the same as multiplying A and B first and then C, which is the same as multiplying B and C first and then A. All right, so the elements must be such that associativity is a property of a group. Also, for a group to be defined, any product, any product, the result of a product must be an element. of the group, of the set, if you prefer, of the set G. All right. So if you multiply A and B, you'll get a C. For instance, A, B, and C, all of them are in G, in the group. All right. All of them are in G. So you cannot have a group if you multiply picking up two elements of the set A and B, and the result is some C which is not contained in the set. All right, so for a group, the product of two of its elements is also an element of the group. For a group, you always need to have an identity. There is an identity element such that if you multiply this element, which is usually called the E in group theory, E times any other element A is equal to A times E, which is equal to that element. All right. Some more evolved theories of groups are concerned with defining the identity operating by the left or by the right, and the operation is only in one of the ways, but I don't think it can be defined as a group. Okay, in group theory, in general group theory, the identity is defined both ways, from the left and from the right. So you this is the in many groups this is the only element which commutes with any other elements of the group. Of course, you can have more than one element commuting with the other elements, but at least one commute with any other element, and this element is the identity of the group. So this is called E, the neutral element of the group. Also, let me write it here. Every element has an inverse, all right? Such that if you multiply that element by its inverse, which I will call a to the minus 1 here, okay, if you multiply any element by its inverse in any order, you'll get the identity, all right? So a group is defined by this set of properties. It's a set of elements satisfying these properties here, right? So this is the definition of a group. If you don't have the inverse, it is not a group. If you don't have an identity element, it is not a group. If you don't have the closure property, which corresponds to that the fact that any product is inside the group, results in an element which is inside the set, is pertaining to the set. And if it's not associative or it is not associative, it is not a group. If any of these operations is not satisfied, you are not dealing with a group. You are dealing with another mathematical entity, but it's not a group. All right, so you need to satisfy all these properties here. It must be associative. It must satisfy closure. It must have an identity element, and any element must must have an inverse, right? Okay, there are groups which are commutative, so groups can be classified according to some specific features. Specific features. So, for instance, they can be dis discrete or continuous. All right. Any continuous group is composed by an infinite set of elements. So, in general, the group is a set of elements, the identity, some A and B and C, which cannot be numerated. All right, so there is a continuous parameter, so called the group G is parameterized by some function of some continuous variable. So all the elements are parameterized by a continuous parameter. All right, and in continuous groups, there are compact groups which are more important for us in some aspects, just to deal with rotations, and non-compact. So for instance, a compact group is that one where you have a closed region of the parameter which specify all the elements. So for instance, from 0 to 2 pi, if it is associated with an angle of rotation, for instance, any value of angle greater than 2 pi can be related to some in some other value in this range from 0 to 2 pi. And non-compact, eventually you have an open bound. So this is closed bounds. You have a open bound for a parameter, so the parameter can be a variable map from 0 to infinity, not from 0 to pi or from 0 to some another value, but an open bound, not a closed. So an open bound here would mean that 2 pi is not included. You can get closer and closer and closer, but never reach the value of 2 pi. All right. So they are continuous, and of course the dimensionality of the continuous groups are always infinite. And discrete groups can be finite or a set of a finite number of elements. So say E, A1, A2, you get to some n minus 1 here because the identity is, or the identity is the A0 element here. Or you have a dimensionality of n, and this n is finite. So you have a finite discrete group. All right. And of course, it can be discrete but infinite. But it still can be counted or numerated. So A1, A2, but it never ends. Right? There are an infinite set of elements. As examples, suppose for finite groups, rotations of a triangle which leave the triangle invariant, right? There are a finite number of operations which can do that. By contrast, you can consider translations of atoms in a crystal, an ideal crystal which extends from minus infinity to infinity. If you translate all the atoms in a crystal by one parameter, which is the interatomic distance, you'll not see any difference in the crystal, and there are eventually an infinite set of operations, of translation operations, but they are still discrete, because in the case of triangles, you can only rotate by 0 or 120 degrees or 240 degrees, and there are only 3 rotations possible. There are also reflections here, so but if you are just considering rotations in a triangle, there are just 3 operations: the identity, a rotation by 120 degrees, and 240 degrees, or minus 120 degrees. No other rotations are allowed. If you rotate the triangle by 60 degrees, the triangle will not coincide with itself. So it's not a possibility. I just forgot to mention that groups are, in the context of quantum mechanics, are related to symmetries, to transformations which make the object, you transform the object, but the object looks like itself before the operation. So it maps the object into itself, right? So there are symmetries of the problem. And in the case of a crystal, you can translate, it's not any translation, but you can translate, say this is the atom 1, 2, 3, 4. You can translate the 1 here, the 2 here, and the 3 here, and the 0 will be here. And if it's a crystal, you cannot see any difference because it's infinitely extended over space, this set of points. But you cannot translate by any other value than A, which is the interatomic distance. So it's discrete. All right. There are only translations by an amount corresponding to this A or multiples of that distance. You cannot translate by any X, because if you translate this any other amount than A, you will put the points, this point will not coincide, and in this way it is not an allowed translation. So there are finite groups and infinite groups. All right. And also you can categorize the groups according to commutation properties. So if elements, and it can be used for this definition for discrete or for continuous. All right. So it's another classification. If elements commute, all the elements, okay, of the group commute with each other, so the operation is commutative, the multiplication you define is commutative, the group is said to be abelian or commutative. All right. So any element commutes with any other element of the group, so the commutator is 0. All right. And if the elements do not commute, it is said non-abelian. So in this case, in general, the commutator of any elements is different from 0, right? This is very important. Both cases are very important in physics. Also, discrete groups and continuous groups are very important in many branches of physics. All right. also an important, without proof, an important theorem in group theory is that any group can be represented or can be mapped by matrix algebra. Okay, by matrix algebra with multiplication. The definition of a multiplication matrix product. And in particular, you can represent any group by unitary matrices. There is a theorem which states that, all right? But I will not prove that statement. So any group can be represented, the set of elements can be mapped, can be represented by matrices, all right? So let us see some examples, perhaps not using matrices. Some examples. Integers, the set is the integers, okay? The Z set, the set of all integer numbers from minus infinity to infinity, including 0. All right, this is the set. And our multiplication is sum, or this symbol here, for our group operation. So the group operation is the sum of two numbers. Notice that it follows, it satisfies all the requirements of a group. It is associative because you can sum 0 plus 1 plus 3, for instance. And in this case, you can associate 0 plus 1 and in the next step sum the 3, or you can perform 0 plus 1 plus 3. So you don't need to specify what is the order for the sum of integers. You can just write it 0 plus 1 plus 3, and it will produce 4. So 4 is an element of the set, which is contained in the group, in the set of elements. So it is associative, and the result of any operation, for instance, minus 2 plus 1, you'll find out this is minus 1. Minus 1 is in the set. All right, so it satisfies associativity, satisfies the closure of the elements. And also there is an identity element, which is 0, all right? The identity is 0 because 0 plus any other integer, suppose plus 1, is equal to 1 plus 0, which is 1. And you can plug in any other element of the group, and it will produce that element. So 0 plus 0 is 0, all right? So the identity times the identity is the identity, all right? Also, any element has an inverse. For instance, pick 1, right? 1 as the element A. The inverse of A under the operation of the group, which is sum, corresponds to minus 1. So the inverse of 1 under the operation of the group, the inverse is minus 1. Why is that? Because 1 plus minus 1 is the identity, 0, which is the same as doing the operation in the reverse order, all right? It's also 0. So it satisfies all the requirements for being considered a group, all right? It is not a group under multiplication because 0 doesn't have an inverse, all right? So under multiplication, you cannot consider it as a group, right? But if you just eliminate zero, okay, if you eliminate zero, you have a group because any element, no, sorry, you do not have the inverse. Even if you consider eliminating the zero, multiplication for this set will not form a group because because the lack of an inverse. So 1 times 2, okay, is inside the set, but 1 doesn't have an inverse, all right? And 2 doesn't have an inverse. One have, but one has, but 2 doesn't have an inverse inside the group, right? So under the sum, it is a group. Under multiplication, the product of integer numbers, it doesn't form a group just because the lack of some of the properties which is required to form a group. All right. There are the modular groups, so you can define sums and to a certain integer, and if sum of the elements is larger than the highest number in the set, you can pick up a particular set of integers from 0 to 3, for instance, but you apply some other rules. They are called modular groups, right? I'll not, I will not spend much any time discussing that because it's just a, it's irrelevant for the moment, right? I guess you could understand this. The example is the integers under multiplication, under sum, right? As the multiplication operation. A, a very famous example of what is Nora Group. If you pick up any set of elements, suppose reals or or rationals, rational numbers, which corresponds to the set of including 0, 0, 1/2, 1/3, 2/3, any number which is a ratio between two integers, right? So you have inverses, negative numbers here also, right? If you consider the operation of division, this operation here, any set of numbers will not satisfy the properties of a group because A divided by B divided by C is not equal in general to that. In general, they are not equal. Therefore, division is not a associative algebra. All right, it's not associative. So any group with any set with division as the operation is not will not form a group because the associativity is not satisfied. All right, so this is another example. Another example which we can consider the set of operations of a triangle. So symmetries of a triangle. If you label the points of the triangle, right? 1, 2, and 3, you label the points. But if you forget the labels, you can rotate the triangle and put it into itself by a proper value of the angle of rotation, right? So in the center, you consider the axis of rotation here. pointing outside the board, right? So this is rotation axis. And of course, you can just consider the triangle in this position, 1, 2, 3, suppose 1, 2, 3, but you can rotate it this way, one, so rotation by 120 degrees. It will let the point 1 becomes the 3, and the 2 becomes the 1, and the 3 becomes the 2. So you're just rotating the points, and the triangle, after the rotation by 120 degrees, will become coincident with itself, but the labels are exchanged. Okay, so they are rotated. After the rotation, the triangle coincides with itself, but the labels are changed. So any group of operations, the discrete groups, can be mapped to a permutation group, a group of permutation of symbols, of labels, all right? So the rotation of 120 degrees is just the permutation of these symbols. A 1 goes here, a 2 goes there, and the 3 here. So it's cyclic permutation here, all right? This is a possible representation of the group using permutations, all right? Now you can also rotate the triangle in the opposite direction. If you rotate this triangle here, if you rotate by minus 120, which is the same as picking up this rotated triangle and produce another rotation of 120, and because the product of these two rotations, it is equal to a rotation by 240 degrees, all right, which is the same as minus 120. The result is the same, all right, corresponds to making the triangle, or you can rotate this thing here in the clockwise sense here. So the 1 goes here, the 2 goes here, and the 3 goes here. Notice that is the same as rotating this triangle here in the counterclockwise sense. So the 3 go here, 2 goes up, and the 1 will be found here. Right? This is after the rotation. So this configuration here, I can always start by the first term and go in the clockwise sense. So I'll find that this is 2, 3, 1. Right? 2, 3, 1 corresponds to that permutation. All right. So I can call this the A element, and this is the B element of the group. And doing nothing with the group is the identity. All right. So A, B, and the identity of the group. All right. Also, you can perform another operations, but from here you can see that A times B is equal to the identity. So if you rotate 120 in clockwise sense and then reverse rotation, you just put your object into the original state. All right, so A times B is equal to the identity. Of course, you can do the opposite way. So this is an abelian group for this operation. The rotations, these rotations are formed in abelian part. So this is also the identity, all right? And the operation of a rotation A times the rotation A, I'll neglect the product operation here. Is the product considering here is the operation of two successive rotations by 120 degrees. This corresponds to B, which corresponds to one rotation by 240 degrees, which is the same as minus 120 degrees. And if you rotate by minus 120 degrees, successively it corresponds to one single rotation by 120 degrees, right? So this is the multiplication table which we can do for this group, only considering rotations. So if you have this table, you can just remember, you can make a table which is in group theory it's called multiplication table. All right, multiplication table. I am just considering rotations. You also have to consider a reflections by mirror planes here. So one, two, and three. If you reflect by a mirror here, the 2 and 3 numbers get exchanged. All right, and you have 3 mirror planes in a triangle. So one is here, and the other is here. So this first mirror plane maintains or keeps fixed the one, this vertex of the triangle, and this other mirror plane keeps fixed this vertex, and so on. All right, and you can perform rotations times reflections. You can expand this group. The group of the triangle has 6 elements, okay, which is the rotation A, rotation B, 3 mirror planes, and the identity. So there are 6 elements, but I'm here just making the multiplication table for the rotations. The rotations of a triangle form a group, a subgroup of the major group of the triangle. All right, there are 6 elements in the group of the triangle, which are A, the identity A, B, and suppose this is C, this is D, and this is F, because the I already used the letter E here. So C, D, and F. There are 6 elements. These 3 elements here form a subgroup, and any reflection form a subgroup with the identity, because if you reflect once and you reflect again by that mirror plane, you just get the identity. There are a lot of rules for group theory. All right, any group can be divided into subgroups. I will not go too much deeper into that, but as I recommended previously, you can consider some books like this or other books in group theory. But you can calculate the multiplication table and notice that the identity, you can consider this operation as first and this is second, but product is this way. So you'll find out E times A is A, E times B is B, A times E is A, B times A is B, A multiplied by A is B, B multiplied by B is A, and A times B is the identity. A times B and B times A is the identity, which we already found previously. So you have just the first the first part of this table, because you need to insert here D, C, D, and F, and here C, D, and F. And I'll let you this to perform this calculation as an exercise. You can complete the table here, the multiplication table for the symmetries of a triangle. It is a discrete group, all right, it's discrete. It has a finite set of elements. It satisfies all the properties of a group, because multiplication of 2 elements, you get a third element, in this case is B, which is contained inside the set of elements. There are only 6 elements in the group of the triangle. You can do the same analysis for the group of a square. A group of a square, you will have reflections by mirror planes. There are four mirror planes. You can perform rotations. There are four possible rotations: 90 degrees or nothing, or 19 degrees. Nothing is just the identity. 90 degrees, 180 degrees, and minus 90 degrees. And you can calculate for a square what you'll find for the multiplication table. And this is it for discrete groups, right? There are molecules which can be described by the triangle group. There are molecules or solids which are described by the square group, and there are a lot of theory in quantum mechanics relating groups with symmetries. So suppose the following. Suppose you have similarity transformations. Remember that a group can always be represented by matrices. All right, the group of the triangle also can be represented. You can find matrices representing the element identity, which is just the identity matrix. The element A, B, C, D, and all that. Any group can be represented by some matrix. And there are similarity transformations, which are operations of matrices. Matrix multiplication always will form for square matrices, for unitary matrices, will form groups. And suppose that you are considering the Hamiltonian. You can consider any other operator, but in quantum mechanics, the Hamiltonian plays a special role, all right? So you can consider the following transformation. You pick a matrix, multiply the Hamiltonian by the matrix, and by the inverse of that matrix, you'll find out a transformed Hamiltonian. Eigenvalues are not changed. Okay, the eigenvalues are not changed by this transformation, so the trace and the determinant of the Hamiltonian are not transformed. They keep the same, all right? But the Hamiltonian, it can look like differently in this basis transformation. It can correspond to a basis transformation, all right? But for S times the Hamiltonian times S minus 1 exactly equal, the matrix looks the same after the transformation. It is said that the set of the elements S, these similarity transformations, which makes the Hamiltonian invariant, right? The set of all transformations of the Hamiltonian matrix or operator, the operations which lead the Hamiltonian to itself, is called the group of the Hamiltonian. All right, this is a very important property. So notice that you can multiply both sides by S here, by the matrix, both sides, and just rearrange the factors so the elements which commute with the Hamiltonian, the matrix transformations which commute with the Hamiltonian, this set of elements of matrices form the group of the Hamiltonian. And they are the symmetries of that Hamiltonian. Because if you transform the basis and your problem looks like the same as previously, you are talking about the symmetry of the problem. All right, it's just like you pick up this cylinder here, you look at the cylinder and you can rotate by some angle the cylinder. Forget about the labels and the colors here, no colors, but suppose it's a perfect cylinder here. You can rotate the cylinder and the situation is the same. You didn't change the physics because you rotated around the z-axis here. So this axis is a symmetry axis of your problem. In the Hamiltonian, it will correspond to a set of transformations which leave your physical system invariant. It looks like the same as previously to the transformation. All right. But now, if you rotate this cylinder here around this axis here, you'll put the system in this new scenario here, and this is clearly distinct from rotating around here. It doesn't change the problem. All right. If you consider, for instance, gravitational energy of the points inside this cylinder, you see a scenario here, a situation here. This point here has a higher potential energy than the bottom here, and you can rotate and you don't change anything in the physics of this problem. But if you rotate this way, you are increasing the potential energy of this point and decreasing the potential energy of that point, and this situation is distinct from that. Considering, for instance, a gravitational potential, all right? So this would be a symmetry rotating around the z-axis would be a symmetry of a physical problem, but rotating around this axis here will not be a symmetry of your problem. And all the transformations, it can be rotations, translations, or eventually more abstract operations which leave the Hamiltonian invariant looking the same as previously as before the transformation are considered the symmetries of the Hamiltonian and form a group which is called the group of symmetries of the Hamiltonian. All right, this is a very important group. Usually, rotations, translations, phase transformations in quantum mechanics also are important. There are transformations which are just discrete, represented by a discrete set of elements. There are transformations which are represented by continuous parameters. Suppose rotations, in this case, you can rotate by any angle, and in this case rotations must be represented by an infinite continuous group, right? Well, I think for a brief introduction to group theory, that's all. And next lecture we will talk about the representations of the rotation transformations. All right, so to finish, I must emphasize that G containing these sets of elements, suppose S1, S2, and of course the identity, which is not to be confused with the energy here. Perhaps it's better to replace by 1 here by the identity. This set of elements, this is the group of the Hamiltonian if the commutator is 0 between the groups of the elements of the group and the Hamiltonian itself. So this is the group of Hamiltonian. And next, we will try to find representations of the rotation group. Okay, next step is find representations of rotations or rotation group, right? This is a job to be done in subsequent lectures. All right. So see you next time.